In today's video, we are going to be studying acid, bases, and buffer system. And here we have the outline of what we'll be discussing. We'll be discussing acids, bases, pH and pOH, pKa and pKb, buffer system, the Henderson-Hasselbalch equation, acidosis, and alkalosis. Okay, now before we consider acids, let's take a look at the autoionization of water. Now, water is able to undergo autoionization, okay, and this simply means that water splits into hydrogen ion, which actually exists as H3O plus, and which is hydronium ion and hydroxide ion. Okay, water has an ionic product. Now this ionic product of water is derived from the equilibrium equation. Okay, the equilibrium equation. Now the equilibrium equation is, so when we have the equilibrium equation, the equilibrium constant, the formula for the equilibrium constant is the concentration of the product divided by the concentration of the reactants. Okay, now this is raised to the power of the mole. Okay, M here refers to the mole of the product and N refers to the mole of the reactant. Now, applying this equation to this autoionization would be considering the concentration of hydronium and hydroxide ion, as well as the concentration of water. However, we can't exactly say water has a concentration because water is a liquid. So the concentration of water is simply 1. And this equilibrium constant can be written as the concentration of the hydrogen ion concentration multiplied by the concentration of the hydroxide ion. And this particular equilibrium constant is known as the ionic product of water. And it has the name Kw. Now the ionic product of water is 1 times 10 raised to the power of minus 14 at 25 degrees Celsius. But our study is based on the human body, and the human body has an average of 37 degrees Celsius body temperature. Okay, and the ionic product of water at this temperature is about 2.4 times 10 raised per minus 14. Okay, it is at 37 degrees Celsius. Now, why does the ionic product of water change based on temperature? Now, the formula for the equilibrium constant is based on temperature. Okay, so when we have product and we have a reversible reaction like this one, and we have reactant on this side. So we have reactant giving rise to the product. Okay, now because temperature has an effect on equilibrium, a change in temperature can lead to the production of more products, and probably a decrease in temperature could lead to the production of more reactants. Okay, so the concentration of reactants and products changes based on temperature, and so the equilibrium constant also changes based on temperature. Okay, now the equilibrium constant of water, as we just saw, is Kw, and is equal to 1 times 10 raised power minus 14 at 25 degrees Celsius. Now, because water is a neutral solvent, it has an equal concentration of hydrogen ion as well as hydronium or hydroxide ion. So the concentration of hydroxide ion is equal to the concentration of the hydrogen ion. However, for an acidic solution, the concentration of the hydrogen ion is greater than the concentration of the hydroxide ion, and for a basic solution or an alkaline solution, the concentration of the hydroxide ion is greater than the concentration of the hydrogen ion. Okay, now there are different acid-base theories. We have the Arrhenius acid and base theory, we have the Bronsted-Lowry acid and base theory, and we also have the Lewis acid base theory. However, for this video, we'll be considering the Bronsted-Lowry's theory of acid and base. Now, the Bronsted-Lowry's theory defines an acid as a proton donor, and it defines a base as a proton acceptor. Okay, proton acceptor. Now, it's good for us to take note of the fact that the hydrogen ion is actually simply a proton. Now, why is this so? Taking a look at the hydrogen atom. Okay, so the hydrogen atom H has 1 proton and 1 electron. Okay, the hydrogen atom lacks a neutron, so it has no neutron. Now, hydrogen ion H plus has this positive charge because it has lost its electron. So once the electron is lost, we are left with just 1 proton. So the hydrogen ion is the same as just the proton. Now, an acid is a proton donor. In other words, it's a hydrogen ion donor, and the base is a proton acceptor, so it's a hydrogen ion acceptor. Okay, so this is the Bronsted-Lowry's definition of an acid and a base. Now let's take a look at pH. Now, for real life solutions, okay, so solutions that we work with, practical solutions and not theoretical solutions, the concentration of hydrogen ion is usually in very minute quantities. So we'll be working with figures like 10 raised power minus 2, 10 raised power minus 3, and so on. Now, the pH scale helps to deal with this issue of having to deal with very little numbers. So the pH is simply the negative logarithm. So the negative logarithm to the base 10 of the hydrogen ion concentration. Okay, pH is equal to negative log to the base 10 of hydrogen ion concentration. So if we have hydrogen ion concentration equal to, take for instance, 1 times 10 raised power minus 4, applying this value to this equation would have that the pH is equal to negative logarithm of to the base 10 of 1 times 10 raised power minus 4. Okay, and according to the rules of logarithm, log of AB is equal to the log of A plus the log of B. Okay, so we would have here that the pH is equal to the negative logarithm. Okay, so putting this in bracket, to the base 10 of 1 plus the logarithm to the base 10 of 10 raised power minus 4. Okay, now log to any base of 1 is equal to 0. Okay, so we'd have here 0. So the pH is equal to negative 0 plus. Okay, so if we have log to the base b of a, these are basic laws of logarithm. Log to the base b of a raised power n, this is equal to n log a of b. Okay, so applying that here would have minus 4 log to the base 10, and then would have negative 0 plus negative 4. Okay, so the pH would be equal to 4. Okay, so rather than working with a value like this, 1 times 10 raised power minus 4, we simply know that the pH is 4. And we have what we call the pH scale. Okay, the pH scale is an open-ended scale. It's an open-ended scale, but for practical reasons, it ranges from 0 to 14. So a pH that is less than 7 is of an acidic solution, and when we have the pH greater than 7, it's of a basic or alkaline solution. Alkaline. Okay, now pH is equal to the negative logarithm to the base 10 of the hydrogen ion concentration. Now, given the pH, we can actually calculate the hydrogen ion concentration with this basic law of logarithm. So, how does logarithm relate to exponential functions? So, given log to the base a of b equals y, this simply means that a raised to the power of y is equal to b. Okay, so this is math coming to play here. So applying that to this particular equation, we would have 10 here represents a, so 10. Okay, before we do that, let's just make the negative on this side. So pH, negative pH is equal to the log of the hydrogen ion concentration. Okay, with 10 here. So this means that 10 raised to the power of negative pH is equal to the hydrogen ion concentration. Okay, so this formula is of importance. Now, it's also good for us to take note of the fact that from the ionic product of water, which is that the hydrogen ion concentration multiplied by the OH ion concentration is equal to 1 times 10 raised power minus 14, given the, which is the ionic product of water Kw, given the concentration of hydrogen ion, we could actually calculate the concentration of OH ion. Okay, so that would simply be the ionic product of water divided by the hydrogen ion concentration, and we could use this to get the OH ion concentration. Now, just like pH, we also have POH. Okay, so POH is equal to the negative logarithm to the base 10 of OH ion concentration. Okay, and this is also of importance. Now, going by our outline, the next thing we have to study is the pKa and the pKb. Okay, now what pH does is that pH gives us an idea of the hydrogen ion concentration, but it doesn't exactly tell us whether the acid is a strong acid or a weak acid. Now, this brings us to the idea of strong and weak acid. Now, a strong acid is an acid that completely dissociates in water. Okay, so it completely dissociates, while a weak acid partially dissociates in water. So for a strong acid, what you have is a single arrow going from acid to ions. Okay, however, for a weak acid, what you have is a reversible dissociation, where we could go from acid to ion and from ion to acid. Okay, now most biological acids are organic acids, and most organic acids are weak acids. Since this video actually relates to the biological system, would be considering majorly the weak acids. So while pH gives us just an idea of the hydrogen ion concentration, pH gives us an idea of the hydrogen ion concentration. However, the pKa lets us in on whether the acid is a strong acid or a weak acid. Now, how does this work? Okay, now given an acid, take for instance, we have an acid HA. Okay, so HA is an acid, and HA happens to be a weak acid. So there's a reversible dissociation here, where we go from HA to H plus and A minus. Okay, so this is a reversible reaction, so to say. Now, given that it's a reversible reaction, we could actually apply the equilibrium constant here. Okay, so applying the equilibrium constant, we would have the products hydrogen ion and A ion divided by the concentration of the acid itself. Okay, now why is this important? This is important because we'll later use this concept in the pKa. Now, because this is an acid, we don't refer to this as an equilibrium constant, but we refer to it as the Ka, or the acid dissociation constant. So Ka is equal to H plus concentration, A minus concentration divided by HA concentration. Now, a large value of HA implies that the numerator is larger than the denominator. So when Ka is high, it means that the numerator is high and the denominator is low. For example, if we have 8 divided by 2, this is 4. Okay, so 4 here represents Ka, which is a high value, and it's as a result of the high value of the numerator. However, if we have 2 divided by 8, we would have 1 over 4, or 0.25, which is a low value, and this is as a result of the low value of the numerator. So when Ka is low, it's as a result of a low numerator and a high denominator. Now, applying this concept here, it means that when Ka is high, we actually have the acid dissociating greatly. Okay, so when Ka is high, it means that the acid actually dissociates well enough. Okay, so we have less concentration of the acid and the ions are more in the solution. However, when Ka is low, it means that we have more of the acid undissociated. So we have a higher concentration of the acid that is undissociated as compared to the dissociated ions. Okay, so this is what this simply means, and this idea is actually applied in letting us know whether an acid is a strong acid or a weak acid, because the strength of an acid is based on how well it's able to dissociate. So a high Ka value means that the acid is more likely to be a strong acid, and when we have Ka value low, it means that the acid is more likely to be a weak acid. So Ka equals the hydrogen ion concentration and then the acid concentration. Okay, now just like pH, we can actually calculate the pKa value. The pKa value is simply the log of the Ka. Okay, so the log of the Ka, negative logarithm to the base 10 of Ka equals pKa. And this applies also for a base. So when we have a base like AOH minus AOH, and this dissociates into A plus and OH minus. Okay, so now we're looking at the Arrhenius definition of an acid just to explain this concept. So we would have the Kb to be equal to A plus OH minus, and then we have the base, concentration of the base, telling us how well it dissociates. So the pKb is equal to the negative logarithm of the Kb value. Okay, these are all values that lets us in on how strong an acid is or how strong a base is, as the case may be. Okay, now very quickly, let's take a look at the buffer. Now, what exactly is a buffer? Now, when we hear the word buffer, what actually comes to mind is like a cushion, like a cushioning effect, a resistance, and that is actually how a buffer works. Now, a buffer resists change in pH. Okay, and it's made of an acid and its conjugate base, as we would see. So a buffer system is made of both the acid, a weak acid actually, a weak acid and its conjugate base, or in general chemistry, a weak acid and the corresponding salt of that weak acid. But for biochemistry here, we'll be considering the weak acid and the conjugate base. Now, buffer or buffer system acts as a reservoir. Okay, so they act as a reservoir of hydrogen ions. Okay, being a reservoir of hydrogen ions, it means that when the hydrogen ion concentration drops, this reservoir of hydrogen ion releases the hydrogen ion. Okay, in order to stabilize the effect. When there's a drop, it releases the hydrogen ion, and when there's an increase in the hydrogen ion concentration, okay, so when the hydrogen ion concentration goes up, this reservoir actually takes in that the hydrogen ions in order to stabilize the pH in general. Okay, so let's take a look at an example of a buffer system. Now, in the extracellular environment, a good example of a buffer system is the bicarbonate buffer system. Bicarbonate buffer system. Now, the bicarbonate buffer system is made of the bicarbonate acid and bicarbonate ion. Okay, so in chemistry, we would call this trioxo carbonate 4, trioxocarbonate 4 acid, and here we have the hydrogen trioxocarbonate 4 ion. Okay, now this is an example of a buffer system. We have a weak acid here and we have its conjugate base. Now, how do we know when we have a conjugate base? So given two pair of substances, so we have H2A and HA. To determine which is the acid and which is the conjugate base, the substance with one less hydrogen, okay, so one less hydrogen is the conjugate base, and the one with more hydrogen would be considered as the acid. Okay, so if we have something like phosphoric acid, PO4, if we take out one hydrogen, we would have H2PO4 minus. So this would be the conjugate base, and it's a conjugate base because if we're to reverse the reaction, it would act as a base. Let's take a look at that. So if we're to reverse this reaction, so we have the acid here, and this is a reversible reaction. So we have H plus and A minus. So this is the conjugate base, right? Conjugate base, and this is the acid. Now, why is it a conjugate base? It's a conjugate base because if the reaction were to proceed in this direction, then this species would act as a base. Okay, so if the reaction were to proceed in this direction, this species is going to be a proton acceptor. So proton acceptor. So it's going to accept the proton in the reverse reaction, thereby acting as a base. So that's why it's referred to as a conjugate base. So basically, the buffer system is made of the weak acid and its conjugate base. And we're going to take a look at the bicarbonate buffer system with this acid and this conjugate base. So this acid is able to dissociate. This acid, first of all, is formed by the reaction of carbon dioxide and water. Okay, so when carbon dioxide reacts with water, carbon dioxide is an oxide of a non-metal. And in general chemistry, we would see that oxides of non-metals are generally acidic oxides. Okay, so acid anhydride. So this reacts and we have an acid as this one. Okay, and this acid is a weak acid. In other words, it dissociates partially. So it dissociates partially into hydrogen ion and HCO3 ion. Okay, so we have something that looks like this. Now, when an acid is added to this buffer system, so this is the buffer system now. And remember, I said earlier that the buffer system acts as a reservoir of hydrogen ion. Now, when an acid is added into this buffer system, an acid would generally increase the hydrogen ion concentration. So it's as good as adding hydrogen ions into this system. Now, here comes a concept from general chemistry, and it's Le Chatelier's principle. Le Chatelier's principle. Now, according to Le Chatelier's principle, when a system is at equilibrium, when stress is applied to a system at equilibrium, and this stress could be in the form of change in pressure, change in temperature, or change in concentration. Okay, so when this stress is applied to a system at equilibrium, the equilibrium would shift in a direction to stabilize or to attain a new equilibrium. Now, although it seems a bit complicated. It's actually a very simple concept. Okay, so basically what happens is you're adding an acid. Okay, you're adding an acid, you're increasing the hydrogen ion concentration. Because this is an equilibrium system, the equilibrium would move in a direction to decrease the hydrogen ion. So you're trying to increase, but the system will try to decrease the hydrogen ion concentration. Now, taking a look at this reaction, you would see that if the reaction were to proceed in the forward direction, we would have an increase in hydrogen ion. However, if we were to proceed in the reverse direction, we would have a decrease in hydrogen ion, and that is the direction in which the system is going to move. So the system is going to move in the reverse direction, that is from here to here, in order to take up, in order to engulf, so to say, this hydrogen ion that is being added. Okay, so and this also makes sense because now when we add these hydrogen ions into the system, so we have a lot of hydrogen ions in the system, and we also have HCO3 ions in the system. Now, from collision theory, an increase in concentration leads to a rise in the rate of the reaction. So these bicarbonate ions are now able to collide more frequently with the hydrogen ions. Okay, they are able to collide more frequently with the hydrogen ions, and so they are now able to produce the acid that we have here. So there's a general decrease in the hydrogen ion concentration. That's how the buffer system works. Now, when you add a base to the system, so what the base does is that the base is a proton acceptor. Okay, so it's a proton acceptor. Okay, now being a proton acceptor, when we add a base to this system, what happens is that the base tries to soak up or take up the hydrogen ions. So there's a decrease in the hydrogen ion concentration. Now, according to Le Chatelier's principle, what the base is trying to do is that the base is trying to decrease the hydrogen ion concentration by reacting or by accepting the hydrogen ion. It's a proton acceptor. However, the equilibrium would move in a direction to counteract this effect. So the equilibrium would move in this direction. So from here to here, and more hydrogen ions would be created. So there's an equilibrium, there's a balance in the system. This is how a buffer system works. So it acts as a hydrogen ion reservoir, releasing hydrogen ions when needed and taking them up when they are in excess. Okay, so this is an example of a buffer system. Another example of a buffer system is the phosphoric acid buffer system, and the phosphoric acid buffer system is also an important buffer in the intracellular environment. Okay, so in the intracellular environment, the phosphoric acid buffer, so we have H2PO4 minus as well as HPO4 2 minus. Okay, now we have seen the buffer system. Let's briefly take a look at the Henderson-Hasselbalch equation. Now, the Henderson-Hasselbalch equation is an equation that is used to calculate the pH of a buffer. Now, we have what we call the buffer capacity. So the buffer capacity is the amount of acid or base that a buffer is able to take up without a significant change in pH. So we have the buffer system, and you're adding your acid, you're adding your base, and it's resisting all of these changes in pH. However, there's a capacity at which it can no longer resist this pH change, and so there's a change in pH of the buffer system. This is the buffer capacity. Okay, it's the amount of acid, the maximum amount of acid or base that a buffer can contain without a significant change in pH. Now, the Henderson-Hasselbalch equation, as I said earlier, helps us to calculate the pH of buffer system. And how does it work? Now, from the Ka value, where we have an acid Ha that dissociates in this reversible reaction into A minus and H plus. Okay, so according to the Ka is going to be equal to the H plus ion concentration, A ion concentration divided by the acid concentration. Okay, now notice that this is a buffer system. Okay, this is a buffer system because what do we have here? We have here an acid and we also have the conjugate base. Okay, so this is a buffer system. So the Henderson-Hasselbalch equation helps us to calculate the pH of buffers. So coming down here, we have Ka equals H plus concentration, A minus concentration divided by the acid concentration. Okay, so now we want to isolate the hydrogen ion concentration because it's the hydrogen ion concentration that actually helps us to calculate pH. So this simply means that the hydrogen ion concentration by change of formula is equal to the Ka multiplied by the acid concentration divided by the conjugate base concentration. Okay, this is by change of formula. Now we want to find the logarithm of both sides. Okay, so taking the logarithm to the base 10 of both sides would have log of the hydrogen ion concentration is equal to the log of the Ka multiplied by H plus divided by A minus concentration. All of this is in concentration. Now, laws of logarithm, log A B is equal to the log of A plus the log of B, and log of A divided by B is equal to the log of A minus the log of B. It's good for us to keep this in mind. Now, applying that rule on this side, would have that the log of the hydrogen ion concentration is equal to, now notice that Ka actually multiplies this entire expression. Okay, so we would have log of Ka plus the log of Ha over A minus. Okay, now moving on, we have that log of Ha log of Ka plus the log of Ha over A minus. Okay, so next, pH is equal to the negative logarithm of the hydrogen ion concentration, right? So we want to have a negative value on this side. This simply means that we'll multiply the entire expression, the entire equation, by a -1. So multiplying the entire equation by -1 would have negative logarithm of hydrogen ion concentration equal to the negative logarithm of Ka minus the logarithm of HA divided by A minus. Okay, now this expression on this side is pH. Okay, so this expression is pH. So pH is equal to this expression. Remember, negative logarithm to the base 10 of Ka is the pKa value. So pKa. Now we have minus the logarithm of acid, concentration of acid over the concentration of the base. Now let's consider this expression as it is. Okay, so considering this expression, we know that logarithm to the base b of a raised to the power of n is equal to n logarithm to base b of a. Okay, now comparing this to this, what we have is n here is actually represented by -1 on this side, so we have an invisible 1 here. Okay, so it means that we can actually rewrite this expression as log of HA divided by log of A minus raised to the power of -1. Okay, because this rule applies. Now since it's raised to the power of -1, if we have 1 over 2, or take for instance we have 3 over 2 raised to the power of -1, it's the same thing as 2 over 3. Okay, so applying that concept here, what we have is that pH is equal to pKa plus, okay, so we have plus now, the logarithm of A minus, because we now have the -1 here and we have the plus value here, okay, divided by HA. Okay, so we can rewrite this as the pH is equal to the pKa plus the logarithm of the concentration of the base divided by the concentration of the acid. Okay, that's because from here we have this to be the base, we have this to be the base, and we have the conjugate base, and we have this to be the acid. Now this is the Henderson-Hasselbalch equation. Now the human body is made up of cells, and these cells are made up of proteins and enzymes and a lot of other structures and substances. Okay, now what happens is that enzymes are very specific. Enzymes are special proteins that help to catalyze reactions, and they are very specific. They work at specific pH, they work at specific temperature. So it's very important to maintain the pH of the human body, okay, because a change in pH could essentially denature these proteins and these enzymes. Okay, now acidosis is of two types. Okay, so we'll be considering two types of acidosis. We have respiratory acidosis and metabolic acidosis. So metabolic acidosis. Now respiratory acidosis, or acidosis in general, actually results from an increase in the hydrogen ion concentration of the body. So when there's an increase, an unusual increase in the hydrogen ion concentration of the body, then acidosis sets in. Now, respiratory acidosis results from certain respiratory diseases. that lead to insufficient expulsion of carbon dioxide. Now remember, as we saw in the bicarbonate buffer system, carbon dioxide reacts with water to give an acid, okay, and this acid dissociates to give hydrogen ions. Now when there is a respiratory disease that leads to insufficient expulsion of carbon dioxide, this respiratory disease could be pneumonia or asthma and so on. Such respiratory diseases could actually lead to an unusual increase in the hydrogen ion concentration and basically the pH, a decrease in pH. So maybe from a pH of 7 to a pH of 6.9 and so on. This is a significant enough change to lead to a lot of hazards in the body. Okay, now this is respiratory acidosis, when there's insufficient expulsion of carbon dioxide. Now metabolic acidosis results from certain kidney diseases. Now the kidney works by ultrafiltration and reabsorption. So the kidney helps to reabsorb certain ions that are needed in the body. So when there is a drop in hydrogen ion concentration, the kidney tubules help to reabsorb this hydrogen ions. When there's a decrease in the base or bicarbonate ion, the kidney tubules help to reabsorb these bicarbonate ions. However, certain kidney diseases make the kidney tubules to be permeable, very permeable, and it allows for the free passage of these ions. Now when there is a decrease in the bicarbonate concentration, okay, when there's a decrease in the bicarbonate concentration due to certain diseases, certain kidney diseases, it could lead to metabolic acidosis. Next is alkalosis. Okay, now alkalosis is an unusual rise in the concentration of the base. Okay, so essentially we have an increase in pH. So the pH could shoot from 7 to say 7.2. Like acidosis, we also have alkalosis. So we have respiratory alkalosis. So respiratory alkalosis could result from hyperventilation. So when you're taking in excessive oxygen, you're breathing in excessively, and so you're breathing in excessively and breathing out excessively also. So there is an excessive expulsion. So there's an excessive expulsion of carbon dioxide. This excessive expulsion of carbon dioxide means that there would be a drop in the hydrogen ion concentration, and therefore there would be an increase in pH. Okay, so from 7 to say 7.2. And then we also have metabolic alkalosis. Metabolic alkalosis could result from vomiting of the stomach acid. So of course the acid is decreasing and the pH shoots up. Okay, all right, so according to our outline, we have come to the end of the video. So far we have discussed acids, bases, pH and pOH, pKa and pKb, buffer, Henderson-Hasselbalch equation, acidosis and alkalosis. If you enjoyed this video, please give it a thumbs up and don't forget to subscribe. Thank you for watching till the end, and sorry for the background